Now let us apply the Schrodinger wave equation to simple harmonic oscillator. I hope you are now familiar and comfortable with the meaning and definition of a simple harmonic oscillator and what is simple harmonic motion. So what is simple harmonic motion? Okay, a simple harmonic motion is a motion which obeys Hooke's law. Okay, what is Hooke's law? The restoring force acting on the particle is directly proportional to the displacement of the particle from the equilibrium position. So a simple harmonic motion obeys Hooke's law. What is Hooke's law? The restoring force acting on the particle F, I write it as F with a subscript x, because we know that the force depends on position. So Fx is directly proportional to minus x. Okay, or if I take it as equation 1, force is nothing but mass into acceleration. So mass into acceleration is double differentiation of the displacement with respect to time. Okay, velocity is, if x is the displacement, t is the time, velocity is dx by dt. Rate of change of displacement with respect to time is called velocity. Acceleration is rate of change of velocity with respect to time, that is nothing but d by dt of velocity is dx by dt. So acceleration is d square x by dt square. So d square x by dt square is nothing but the acceleration of the particle. So mass into acceleration is nothing but the force. So this is directly proportional to minus x. So any motion, to and fro motion, which obeys this equation, which is a law called as Hooke's law, is called as a simple harmonic motion, and that object is called as a simple harmonic oscillator. If we replace this proportionality as we had done in the previous video, we get mass into d square x by dt square is equal to minus k into x, where k is the force constant of the bond. Okay, let us rearrange this equation. Okay, on rearranging we get therefore d square x by dt square plus k divided by m into x is equal to 0, into x is equal to 0. This is nothing but rearrangement of this equation. Let us take it as equation number 2. Okay, here when I say m, so which atom's mass I have to substitute here. For example, if I am taking HCl molecule, there are two atoms. Okay, so there are two masses, therefore, so mass of which atom I have to substitute. Okay, strictly speaking, the vibration of HCl, it is a two particle problem, and I had already explained, whenever there is a two particle problem, what we do is we replace a simple two particle problem by a hypothetical single particle problem, and the mass of that single hypothetical particle is given by reduced mass mu. So strictly speaking, here we should not have m term, here we should have mu, which is the reduced mass. Okay, reduced mass, assuming that when the HCl molecule is vibrating, both a hydrogen atom as well as chlorine atom are displaced from their respective equilibrium position. But if we are assuming that the position of chlorine is fixed and it is only a hydrogen atom which is moving to and fro from its equilibrium position, so it is actually the hydrogen atom which is exhibiting simple harmonic motion. So in such case, here m represents the mass of hydrogen atom. So if I am taking a heteronuclear diatomic molecule, m represents the mass of the lighter atom present inside the molecule. But strictly speaking, it should be mu. Okay, because however heavier is the one of the atom, when the molecule vibrates, actually both the atoms are displaced from their equilibrium position. Okay, so we will use with this simple expression m. So here m represents the mass of the lighter atom. In this case, it is the mass of the hydrogen atom. Okay, and we will not go into detailed mathematics here. Okay, as I already told you, when we discuss rigid rotator in our syllabus, we are not supposed to go into all the detailed mathematics, how to solve all these equations. That is none of our business here. If you go to higher level, that is if you join MSc chemistry or MSc physics, then there you will study all the mathematical solutions. So here we are not concerned with the solution, how to solve these equations. We are only interested in the final solutions or final expressions. Okay, so this is a very simple differential equation which can be solved in a straightforward manner, okay, which we need not solve here. And so once we solve this differential equation, it can be observed that the force constant K, its value turns out to be K is equal to 4 into pi into nu square into m. Okay, so this is the expression for force constant. Force constant K is equal to 4 into pi into nu square. Nu is the frequency of vibration, and into m, where m is the mass of the particle. Okay, that is, in this case, that is the mass of the hydrogen atom. And as I already told you, the potential energy V, or I will write it as Vx, because potential energy depends on the displacement of the particle. So the potential energy of the system where the particle is subjected to a simple harmonic motion, that is, it is experiencing a force given by this equation. The potential energy is given by V is equal to half into K into x square. This is the expression for potential energy. Let us take it as equation 4. So far, whatever I have written on the blackboard, it is already discussed in the previous video. So now what we will do is, let us substitute equation 3 in equation 4. Then we will get an expression, much better expression for potential energy, which is half into K is 4 pi nu square m into x square. Therefore, potential energy Vx is equal to 2 pi nu square m into x square. So this is the expression for the potential energy of the particle. Okay, I made a mistake here. It is 4 pi square. Okay, 4 pi square, pi square, pi square. So 2 pi square nu square m into x square. This is the potential energy for a simple harmonic oscillator. Now let us write the Schrodinger wave equation. Since this vibrational motion is a one-dimensional motion, and if we assume that this vibration happens along x-axis, then we can write this one-dimensional Schrodinger wave equation. The general time independent one-dimensional Schrodinger wave equation. Okay, this is the general form of equation, is d square psi x, because it is only concerned with the x-axis. So d square psi of x, or d square psi x, divided by dx square plus 8 pi square m by h square into e minus V, potential energy, which depends on the position x, into psi x is equal to 0. Here you can write either psi of x or psi x. Okay, the meaning is one and the same. So this is the general Schrodinger wave equation. Now if I substitute this expression for potential energy here, then what we would have done is, we would have constructed or written a Schrodinger wave equation for simple harmonic oscillator. So let us substitute equation 5. Substitute equation 5 in equation 6. Remember, equation 5 is applicable for a simple harmonic oscillator. So if I substitute this term here, then d square psi x divided by dx square plus 8 pi square m by h square into e minus e minus 2 pi square nu square m into x square into psi x is equal to 0. So what is equation number 7? Equation number 7 is the Schrodinger wave equation for a simple harmonic oscillator. This is the general Schrodinger wave equation, one-dimensional Schrodinger wave equation. This is the Schrodinger wave equation for a simple harmonic oscillator. So equation 7 is the Schrodinger wave equation for simple harmonic model or simple harmonic oscillator model. This is a differential equation, okay, but solving this differential equation, one dimensional differential equation, is very complicated. Okay, if you go back to particle trapped in a one dimensional box, which is also a one dimensional system or one dimensional problem, there solving the Schrodinger wave equation was very simple. Why it was simple? Because the potential energy of the particle was constant there. It did not depend on the position, it was independent of position. So potential energy was a constant. But here, if you look at this term, this is not a constant. Potential energy is not a constant. It depends on the position of the particle. So this is not a constant term, okay, because this varies with respect to x position. So solving such differential equation is not straightforward, okay. So the way we solved Schrodinger wave equation for particle in one dimensional box, which was a very straightforward solution, this is not a direct solution. So this is a very complicated solution which we fortunately need not discuss, okay. But please do remember that the method, there are two methods to solve this type of differential equation, and one of the method is called as power series method, okay. So you just remember the name of the method. Equation 7 or such type of equations, okay, can be solved by a method called as power series method. So equation 7 can be solved by power series method, okay. What is power series? We will not go into those discussion, that is not point of interest to us. What is interested is, after applying this power series method and doing many mathematical exercise, we finally end up with the two expressions that are the solutions. One is the expression for the energy, total energy of the simple harmonic oscillator. The other is the expression for the eigen wave functions. So first let us write the expression. So after solving the Schrodinger wave equation by using this method, the expression for total energy E is equal to, okay, or I will write it as En is equal to n plus half into h into nu, or you can also write it as EV, okay. This is a somewhat standard way of writing. EV is equal to V plus half into h nu, okay. This is the expression for the total energy of the simple harmonic oscillator, or the vibrational energy of a diatomic molecule of such as HCl, okay. So what is H here? You already know it. It is the Planck's constant. Nu is the characteristic vibrational frequency of the molecule. N or V is called as vibrational quantum number. Okay, you know that whenever you are solving Schrodinger wave equations, we come across different types of quantum numbers. And why this quantum number arises? The quantum number arises because of the boundary conditions. So here also we are applying certain boundary conditions. What are those boundary conditions are not required here. So because of some boundary conditions that was applied while solving these equations, it resulted in this quantum number which is called as vibrational quantum number. And the values this vibrational quantum number can take is always an integer starting from 0. Okay, so the lowest value of n or v is 0, and it can take only positive integral values. So that is why it is a quantum number because its value is restricted to certain values. Okay, as I already told you many times, when a Schrodinger wave equation is solved, we get two information. One is the total energy, another is the expression for the eigen function. Okay, so how to obtain this is again not required. We will directly write what is the expression for the eigen function. The normalized, okay, it is already normalized. The normalized eigen function for the simple harmonic oscillator is given by psi n x. Okay, I'll write it as psi n of x. Okay, that is the wave function depends on n, that is the value of the vibrational quantum number, and it also depends on the position of the particle, is equal to some complicated expression which you have to memorize, square root of alpha divided by 2 to the power n, that is the vibrational quantum number, into n factorial into square root of pi whole to the power half, okay, into e to the power, that is exponential, or e to the power minus half alpha x square into h n, okay, into h n. What is alpha here? Let us define. Alpha is nothing but defined as 4 pi square nu into m divided by h. All the terms present in the right hand side is known to you. Nu is the frequency, m is the mass of the particle which is subjected to vibrational motion, h is the Planck's constant. Okay, and this term hn is a polynomial. Okay, it is a mathematical polynomial called as Hermite polynomials. What is this Hermite polynomial? What is its expression? Okay, what are its different expressions? We will not discuss about those. Okay, all those will be done in your postgraduate course. So this is the expression that you have to remember. Okay, so we will not go for analyzing this equation. In fact, what we will analyze is, we will plot this as a graph. We will plot a graph of wave function versus position. Okay, and we will try to understand or analyze that graph. Okay, this cannot be directly analyzed, this equation cannot be directly analyzed, but the corresponding graph, okay, obtained from this equation, we will try to analyze that graph. Okay, and also we will try to analyze this equation. For analysis, what we will do is, we will plot this graph, okay, as we did in particle in a one-dimensional box. Remember, in the particle in the one-dimensional box, we plotted wave function versus x. Another plot is square of wave function, that is psi square versus x, that is nothing but the probability graph. Okay, here also we will have two plots. One is wave function versus x, the other is the square of the wave function versus x, which is a measure of probability. Okay, and try to understand or interpret those graphs. Okay, and all those things we will do in very simple details. Okay, we will not go into deeper meaning of all this. So this y-axis represents the scale of energy. Okay, scale of energy, and I am plotting this wave function versus x. So this represents, okay, x, this represents higher energies. Okay, in the background, what I will do is, I will plot the potential energy curve. Okay, this is the background. Okay, I will not take so much space because I have to plot two graphs. Okay, so this is the background. of potential energy graph. What is potential energy graph? You know that potential energy V is equal to half into K into x square. So V depends on position as square of x. So if I plot potential energy versus x, the nature of the graph will be like this. So this is a potential energy curve. So this represents the position, the displacement. So this is the equilibrium position, x is equal to 0. As we see that as the energy increases, okay, so this is the equilibrium position. As the energy increases, what happens to the size of the displacement? The size of the displacement also increases. The amplitude of vibration also increases. So as you increase the energy of the vibrating molecule, it means there is an increase in amplitude. So as you increase the vibrational energy, the molecule starts vibrating with greater amplitude, with the same characteristic frequency but with greater amplitude. So as the energy increases, the amplitude of vibration also increases. So that is this why this graph is like a V-shaped graph. Okay, so this width increases, it means the amplitude of vibration increases. Okay, so I will take this as a background reference, and above this I will try to plot wave function versus x. First let us plot the wave function for the lowest energy. Lowest energy means I have to substitute the lowest value of n. The lowest value of n is 0. So if I substitute the lowest value of n, that is 0, the lowest energy is half into h nu. So remember, the lowest energy is not 0 here. So lowest energy is half into h nu. So if I consider this as 0 of energy, the particle will never have 0 energy. Okay, with respect to vibrational motion, the vibrational energy cannot be equal to 0. The minimum or the lowest energy it can have is E0 is equal to half into h nu. Okay, so the lowest energy the particle can have, the vibrational energy the molecule can have, is E0 is equal to half into h nu. Okay, so this is the lowest energy scale. Okay, here now I will plot wave function versus x with n is equal to 0. The nature of the plot is like this. It is a half wave type of plot. It is a half wave type of plot, but if you see here and compare it with particle in a one-dimensional box. Okay, in particle in a one-dimensional box, okay, potential energy was uniform. Okay, throughout the box potential energy was uniform. Here the potential energy is not uniform. Okay, or not a potential energy, the length of the box is not uniform. Okay, it increases as energy increases. Here it is uniform. So when n was is equal to 1, that is the lowest state, wave function was something like this. Wave function was something like this. Okay, something like this. So what we see here is the wave function becomes 0 at the boundary points. So here the wave function becomes 0, here also wave function becomes 0 because of certain boundary conditions. But here what we observe that here the wave function does not become 0 at these two points. The wave function in fact, okay, crosses this barrier. Okay, this is called as classical forbidden region. Classical forbidden region. This is also classical forbidden region. So any point outside this curve is called classical forbidden region. It means the particle cannot be located outside this region. It should be always vibrating within this region. But what do we see here from quantum mechanics is there is, okay, a partial wave function even outside this classical forbidden region. Okay, this in fact raises a new phenomenon in quantum mechanics called as quantum mechanical tunneling. It means according to classical mechanics, the particle is restricted to certain position, it cannot move beyond that certain position. As I already told you, when the particle is vibrating, it can always vibrate between the maximum amplitude. It cannot exceed, its displacement cannot exceed the maximum amplitude. Okay, that is forbidden. But what we are seeing here is there is some residual wave function beyond that forbidden region. Okay, such type of results can be expected only in quantum mechanics. In classical mechanics you cannot expect such result. Such phenomenon where there is a residual wave function even outside the forbidden region is called as tunneling, which we will not discuss in detail. So this is a similar wave, but there is some difference between these two waves. This is also half wave, this is also half wave, but here this half wave at these two boundaries it becomes 0, the wave function becomes 0, but here the wave function does not become 0, it slowly decays and it becomes 0 only at x is equal to minus infinity and at x is equal to plus infinity. Okay, so this is the plot of wave function at the ground state or the lowest energy state. Similarly, if I plot the wave function for the next energy state, okay, for the next energy state, let us calculate the energy. Next energy state means n is equal to 1 or v is equal to 1. When n is equal to 1, 1 plus half, that is 3 by 2 into h nu. Okay, so it is somewhere here. So E1 is equal to 3 by 2 into h nu. Okay, and we see here that as the energy has increased, the width of this background graph has also increased. It means now the particle can vibrate with greater amplitude. So on this, let us plot wave function versus x for n is equal to 1. Okay, here we have a single curve, that is a half wave. When n is equal to 1, we get two waves. It is something like this. Okay, so you have two half waves or a single wave, and again this wave or the value of the wave function does not become 0 at these two boundaries. It actually decays, slowly decays to 0 at minus infinity and plus infinity. Okay, it only becomes 0 only at minus infinity and plus infinity. So there is some residual wave function even beyond this forbidden region. Similarly, you can plot the corresponding wave function graph plot for the next energy. The next energy is when n is equal to 2, 2 plus half, that is 5 by 2 h nu. 5 by 2 into h nu. Okay, here we had two half waves, so the next should be three half waves. So the graph is something like this. Okay, something like this. Similarly, for n is equal to 3, E3, okay, if I plot E3, which is 7 by 2 into h nu, the graph should contain four half waves. Okay, it should contain four half waves and so on. So similarly, you can plot the corresponding plots for n is equal to 4, 5, 6, etc. Okay, what is more interesting is plot of psi square versus x, and you have the experience of plotting wave function psi square versus x. What we have to do is we have to just take the square of this graph. So whatever negative phase you had here, if I take the square, it becomes positive. Okay, so plotting psi square versus x is now very easy. Okay, so again I have the same energy levels, E0, E1, E2, E3. Okay, so again I will plot this potential energy graph. Okay, again this is the equilibrium position, x is equal to 0, this is x. Okay, so for the lowest energy, if I take this square, the graph is again something like this. For E1, if I take the square of this, something like this. Okay, the graphs that are drawn are not perfect. Okay, for n is equal to 2, this is E0, this is E1. Now for n is equal to 2, graph will contain 3 maximas. Like this. Similarly for E3, that is when n is equal to 3, you get 4 maxima. Okay. And you see that here these two maxima has greater height compared to this. Here also these two maxima, which are very close to the extremes, okay, has greater height compared to these two maximum at the center. Okay, so this is how the nature of psi square versus x looks like for a simple harmonic oscillator. Now let us make some comment on this graph. Okay, here since we are plotting psi square versus x, psi square we know that it represents probability. So this graph is actually a plot of probability as a function of position, and at the ground state the probability is maximum at the equilibrium position. So according to the results of quantum mechanics, for a simple harmonic oscillator in the ground state, the maximum probability of finding the particle is at the equilibrium position. But as the energy of the particle, vibrating particle increases, as the vibrational energy increases, what we observe is the probability of finding the particle shifts from the center to the extreme sides, okay, to the two extreme sides, that is x is equal to a and x is equal to minus a. See here, in the first state, in the exact state, the probability of finding the particle at the center is almost 0, whereas the probability of finding the particle is maximum towards the two extreme amplitudes, maximum to extreme displacement. Okay, so if I increase the quantum numbers at the next higher energy, we see that the maximum probability of finding the particle is more at the two extremes, and the probability of finding the particle at the center is slightly less compared to this. And at when is equal to 4, the probability of finding the particle at the extreme position has increased, and it is probability is very less at the center of the box. So as the energy of the simple harmonic oscillator increases, probability of finding the particle, okay, that probability, maximum probability, shifts from equilibrium position to the two extreme situations, okay, that is x is equal to a and x is equal to minus a. So this is a very important observation. Let us comment on some of the important characteristic features of this term, energy term, which represents the vibrational energy of the simple harmonic oscillator. The first important point that I like to say is the vibrational energy of the simple harmonic oscillator is quantized. Okay, we always have a question whether the energy is quantized or whether the energy is continuous. Here, for a simple harmonic oscillator, the vibrational energy is always quantized. Why it is quantized? Because here n or v, the quantum number, vibrational quantum number, cannot take any value. It can take only integral values. So the first point you have to remember is vibrational energies are always quantized. The second important observation is about the lowest energy. The lowest vibrational energy is when n is equal to 0 or v is equal to 0, and when n is equal to 0 or v is equal to 0, the lowest energy is 0 plus half, that is half h nu, which is not equal to 0. it means there exists a minimum non-zero energy called as a 0-point energy. So there is a 0-point energy with respect to vibrational motion, and the 0-point energy is E0 is equal to half into h nu. Okay, so the lowest non-zero energy, which is called a 0-point energy for a simple harmonic oscillator, is given by half into h nu. What is the meaning of this? If I have a molecule which is vibrating, okay, at room temperature, if I decrease the temperature of the system to 0 Kelvin, then even at 0 Kelvin the molecule will continue to vibrate with a minimum energy which is equal to half into h nu. But what we observed in the rigid rotator discussion, that there does not exist 0-point energy with respect to rotational motion. What does it mean? Where if I have a molecule which is rotating as well as vibrating, so I have HCl molecule which is performing both rotational motion as well as vibrational motion. So if I cool the molecule, that is if I decrease the temperature of the molecule to 0 Kelvin, then at 0 Kelvin the molecule would have stopped rotating because its rotation energy is 0, but it would continue vibrating with this minimum energy equal to half h nu, which is the 0-point energy. The third important feature of this vibrational energy is that the vibrational energies are equally spaced. Okay, remember, rotational energy levels are unequally spaced, whereas vibrational energy levels are equally spaced. How it is so? Let us see. Okay, that I had already shown it, but unfortunately I have rubbed the board, so I will again show it. Okay, so the lowest energy is E0, which is equal to half h nu. Okay, so this is the energy level diagram for the lowest energy. The next energy the particle has is E1. E1 is 1 plus half, that is 3 by 2 into h nu. Okay, 3 by 2 into h nu. The next energy the particle has is E2, which is 2 plus half into h nu, which is 5 by 2 into h nu. The next energy the particle can have is E3, that is 3 plus half into h nu, that is 7 by 2 into h nu. So if you calculate delta E here, which is E1 minus E0, or if you calculate delta E here, which is E2 minus E1, or if you calculate delta E here, which is E3 minus E2. Okay, so wherever you calculate delta E, this difference is h nu. This difference is also h nu. This difference is also h nu. So the space between any two energy levels is same, h nu. Okay, the energy gap here is also h nu, here it is also h nu, here it is also h nu. What does it mean? It means that the vibrational energy levels are equally spaced, which is contrast to what we observed for rotational energy levels. Rotational energy levels are unequally spaced, whereas vibrational energy levels are equally spaced. So there is some difference between the characteristics of rotational energy levels and vibrational energy levels of a molecule. Both rotational and vibrational energy levels are quantized, but vibrational energy with respect to vibrational energy of a molecule, there exists 0-point energy which does not exist for a for the rotational energy of the molecule. The second difference is vibrational energy levels are equally spaced, whereas rotational energy levels are unequally spaced. Okay, so this is some discussion about application of Schrodinger wave equation to simple harmonic oscillator model. This is not the complete discussion. Okay, we have only discussed only certain important points. Okay, the aim of this discussion or lecture was to introduce you to some of the important results of application of quantum mechanics to this particular model. In detail you can study it by referring to any textbook, or if you come to postgraduate course MSc in chemistry, There we will study the complete solution with the mathematics, the complete solution of simple harmonic oscillator. Okay, so with this I conclude this class. Thank you.